Now, can you have your notes prepared? Okay. Now look at the scalar multiplication vectors. Now what is it? Now scalar multiplication vectors is when you have a vector, let's say V. Let's say V. And then you multiply it by a scalar, let's say lambda. In this figure, you can see 2v, or negative 2v. This is when lambda equals to 2, or lambda equals to negative 2. The meaning of it is to keep the same direction, that will multiply by 2. You will keep the same direction and just extend the length to 2 times of its original. So you have this. When lambda is greater than 0, and lambda a is a vector, and is equal to, the magnitude is increased by or decreased according to the value of lambda. So lambda a is lambda times that of a, lambda times the magnitude of a, and then the direction is kept. Now, if lambda is smaller than 0, then lambda times a is a vector, is opposite to a. Like this one is a negative 2a, negative 2v, negative 2v. And then the direction is just the opposite. Okay. Now, if lambda is 0, then lambda times a is equal to the 0 vector. Okay. Now here, please notice that we have these two notations like this. These are the magnitude of a vector, whereas this one is the absolute value of a scalar. So we use the same notation, but they mean differently. Lambda, this denotes the absolute value of lambda. But a, this one denotes the magnitude of a. I guess the names are different for these ones. Like for scalar, it's called the absolute value. For vector, it's called the magnitude. Now for any 0 vector, we denote this vector. This is a notation. This vector equals to a divided by the length of a, or you can write it as a 1 over the length times a represents the unit vector in that direction of a. But this is also difficult to understand, but I'll show you using a figure. Let's say a is a vector like this. This is a. And the magnitude of a is 3. Now, how do you express the unit vector of, this is the unit vector. I call it a, this, a little bloopy. So how do you express a bloopy, this one, the unit vector in the same direction as a? You will take a and then divided by 3, because the length of A is 3. If you divide by 3, then it's 1. So that is the unit vector. Okay? So that's what it is. So whenever you want to get a unit vector, you just use that vector and then you divide it by the length. Next thing. There is a very useful theorem you do use very often when you want to say that two vectors are parallel to each other. If one vector is equal to lambda times another vector, then the two vectors are parallel. Now, for example, this is A, this is 3A, then I know these two are parallel. Now, even when this is A, this is negative A, then they're parallel. Now, this is very useful when you need to show that two lines are parallel, then you probably will show that one vector is equal to a certain number times the other vector. Now, in particular, if the two vectors are joined together, for example, one of the ends that coincide, in this case, AB, the end of AB is the beginning of BC. If they're joined together and they also have this, one vector is equal to lambda times the other vector, then they're not parallel, they're coincide. They're collinear, sorry. They're collinear. Let's finish the classwork. Refer to the vectors in the figure below. Draw each of the following on the same figure. Now, if I have 3A, if I have A like this, how do I draw 3A? Now, remember, you don't have to draw it here. You don't have to start here. You can start anywhere. Now, I will start here. 3A. Okay. How about negative 1 over 2b? Negative 1 over 2b can be here, just half the size, and parallel, and opposite side. Negative 1 over 2b. 2a got plus 1 over 2b. 2a. 2a. 2a plus 1 over 2b. 1 over 2b. I draw it here. 1 over 2b. So it's this way. Use the parallelogram. This will be 2a plus 1 over 2b. Okay. Now 3 over 2b. 3 over 2b. 3 over 2b. This is 3 over 2b minus a. Maybe I drew it somewhere else. It's too close. 3 over 2b. 3 over 2b. And then minus a. So I will draw a here, so they're connected. This is a. So the answer is this. Three over 2b minus a. Okay. Next page. Now the properties of scalar multiplication are as follows. So I have two scalars, lambda and mu. Now if I have lambda times mu times a, it can be lambda times mu first and then multiply a. For example, 3 times 2a equal 3 times 2 first and then a. That is 6a. Okay? Without proving, we just say that. Part B is that it's distributive, which is lambda plus mu times a is lambda a plus mu a. Meaning that, for example, 2 plus 5 times a equal 2a plus 5a. The last one, for the vectors, it's also distributive, which is lambda times a plus b equal lambda a times plus lambda b. So that is 2 times a plus b equal 2a plus 2b. Okay, so if we only consider the addition, subtraction, and scalar multiplication, the vectors basically behave the same way as numbers. Remember, we talked about the behavior in the last chapter. We say that all the matrix, they behave the same way when it comes to addition and subtraction, but with multiplication, it's not the same. But for the vectors, addition, subtraction, and scalar multiplication, they behave the same way, basically. Example 2. The parallelogram ABCD, G is the midpoint of BC, and FE are the points, such that DF equal FE equal EC. So there are two vectors already. A, this vector, and ADB. There are two vectors already. The exercise is to express the other lines all in terms of A and B. Now for your information, with 2D figures, such as this parallelogram, to express all the vectors in this figure, you only need two base vectors. Here A and B are our base vectors. So we'll use that to express everything else. First one is AE. Noticing that AE equal AD plus DE. And DE equal 2/3 of AB. So this is expressed. It's B plus 2 over 3A. Okay. B. G. Noticing that GE equals to, now I will try to use GE. Now GE equals to GC plus CE. Looking at this small triangle, huh? GC plus CE. And GC is equal 1 over 2 AD. And CE equals to negative 1 over 3 B. Oh, sorry, not B. CD. CD, which is BA. What did I do? CE equal, sorry. CE equal 1 over 3 CD, which is 1 over 2 AD. GCAD minus 1 over 3 AB. So the answer is 1 over 2B minus 1 over 3A. Okay? Now you practice the exercise and let me know when you're done. Okay. Now I think you need practice in deciding how do you express AN. I think in the example and in the quick practice, I only use addition. Of course, you can use subtraction, but I only used addition. Now, using addition, you see the technique. Now, if AN, then AM was equal to AB plus BN. So using addition, you're just adding like a mid-stop for this vector. So AB, BN is AN. For MP is MD, DP. Okay. Now, is there any other method? I think so. I think so. But maybe longer, right? Later on, we'll see. Next example. In this figure, ABC is a triangle. Given that DE and are the midpoints of AB and AC respectively, prove a vector equals to another vector. Now, in this question, you must realize that there is a geometry theorem behind it, which is in the triangle ABC, if D and E are the midpoint of AB and AC respectively, then we have DE is parallel to BC, also DE equal half BC. So if DE are midpoints, then DE equal 1 over 2 BC, and DE is parallel to BC. This is, I think you learned it as the midpoint theorem. Okay, and then if you use this theorem and then say, of course, now because of their parallel, then obviously they are one equals to the other one times lambda, and also because the length is 1 to 2, length ratio is 1 to 2, so 1 equals to 1 over 2 times the other one. But that's not the intention. That's not the intention. In this question, you're not supposed to use the geometric theorem result to say, oh, this is true. Now, in this question, you're supposed to apply the multiplication, the addition, subtraction of vector, and show this is true in the vector language. You will find it very easy. So for this, first we need two base vectors. Now I'll call this D. I'll call this AB, one base vector. I call it B. And I'll call this one C, the other base vector. So in this question, let AB be B, AC be C. Okay, so any other vectors must be presented, must be expressed in terms of these two base vectors. So here, for example, BC equal BA plus AC, and that is negative AB plus AC. So that is negative B plus C. So it's expressed. And then DE is 1 over DE is DA plus AE is equal DA is 1 over 2 BA plus AE 1 over 2 AC, and negative 1 over 2 AB plus 1 over 2 AC. That is negative 1 over 2 B plus 1 over 2 C. Okay? Now, because you can say that negative 1 over 2, obviously negative 1 over 2 B plus 1 over 2 C is equal to 1 over 2 negative B plus C. Therefore, DE is equal to 1 over 2 BC. I mean, the vectors, they're equal. Okay. Now, if you compare this, now if you say, oh, this is also a proof of midpoint theorem, if you compare this vector proof with the proof of midpoint theorem using geometry, if you recall the proof for midpoint theorem for geometry, you have to prove similar triangles and corresponding angles are equal and this and that. It's a lot of angles and lengths. But with vectors, if you're using the vectors correctly, the only thing you need to do in this proof is to express. Now, there is express here and then express here. Now, you will find out that in a lot of traditional, the classic geometry problem, if you use vectors and if you successfully express the length, I mean the line segments using vectors, sometimes the results is just right in front of you. This is also why we need to study vectors, because they're so efficient in showing the relation between lines and angles. One moment. One moment. Okay, we're back. Okay. Like I was saying, that in this whole process, you won't see me discussing, oh, what is this angle? What is this angle? Or because these angles are equal, so they're parallel. There's no such thing like that. The only thing we do in vectors is to express, to find out how to write down the vector du, how to write down the vector bc. And if you have done that successfully, then you will see the relation. In this case, there are two relations, parallel relation and the length relation. It can be shown in the vector expression right away. Okay. Now the practice, you can do the practice and let me know. Okay, I see that you are done. You are done. Look at my solution. Now, it's not completely necessary, but I recommend that you do so. That if you have decided that these are the two base vectors I use, maybe you let it out. You say, oh, this is B, this is C. Okay. And then in this question, I think it's easier if you can express BC first. Express BC first. Now, BC can be equal C minus B. Now, if you're faster with this, I think you can do it in one step. BC equals C minus B. But I think this is the first lesson, so let's do it slower. Now, BC equal BAAC, AB equal negative AB, and then plus AC. That is negative B minus C, and negative B plus C. So it's also C minus B here. On Thursday, I discussed this with you. This one is C minus B. If you know the subtraction well, that's C minus B. So if you get BC first, and then AD can be expressed. Now remember AD, here I use AB plus BD. You can also use AC plus CD. Alternatively, AC plus CD should also work. You should get the same answer. Anyway, in the final answer, in the final steps, you should show that AD equal 1/2 B plus C, which is 1/2 AB plus AC. That's it. This question is supposed to be similar to the example, but because it's not so obvious that this is a result we already know. It's not so obvious, but because this formula in the coordinate geometry, we did learn this formula. Now, I want to point out what is the relation between the vectors and the classic geometry. Now, this is the 2D vector, so the classic 2D geometry. So this one, did we learn it before? Yes. Yes. But we didn't learn it in this way, so you may not recognize it. But it is actually the midpoint formula. Not a midpoint theorem, but midpoint formula. Saying that the coordinates of D is equal to the coordinates of B plus the coordinates of C divided by 2. I don't know if you recognize it, but this is what it is. Now here A is seen as the origin. Of course, it doesn't look the same way. Doesn't look it the same way because in this way, in the coordinate geometry, we use coordinates. But in the vectors, we use vectors, but they are the same results in this way. Try to link them. Okay, all I'm saying is that if you want to prove this, it's another skill. It's not another set of skills. If you want to prove it using vectors, then you just need to express the vectors. Okay, next example. In this example, in the figure ABCD is a parallelogram. E is the midpoint. CF to FD is 1, 2, 3. So this is 1, 2, 3. One, two, three, like that. There are two base vectors, P and Q. It's already there. So I'll just highlight them. Express AE. Let me write it here. AE equal AB plus BE. Which is equal to AB plus BE, which is 1 over 2 AD. So that is P plus 1 over 2 Q. AF. AF equal AD plus DF. And DF equal 1, 2, 3, 4. 3/3 of AB. 3/4 of AB. 3/4. 1, 2, 3, 4. Yes. 3/4 of AB. So this is equal to Q plus 3 over 4 P. Okay. Part B. If P equal 4, P equal 4, so this length is 4. Find 2AE minus AF, the length, 2AE minus AF. First of all, 2AE minus AF. Right now, I'll just do substitution. I won't even look at the figure because it gets too complicated if I look at the figure. If they're expressed, then I'll just look at vectors. So 2AE minus AF. And then I will simplify. That is 2P plus Q minus 3 over 4P. And the answer is 5 over 4P. Right? Okay. So it's 5 over 4P. Therefore, the length must equal 5 over 4P length. In this case, 5 over 4 times 4. That's 5. Okay. Part B. B2. Find the unit vector which is parallel to this vector. No. Sorry. The question is wrong. The question is wrong. Find the unit vector which is parallel to this vector. No magnitude, just 2AE. AF. Parallel to this vector. Not the magnitude of this vector. Parallel to this vector. So I already know the length is 5. So the required unit vector, which is equal to 2AE minus AF. Now here I will use this symbol as the unit vector symbol. Now you don't have to write it. It's not in the textbook, but it's in other textbooks. The unit vector is equal to 1 over 5 times the vector, which is, the vector is found, right? 5 over 4P, which is 1 over 4P. It makes sense because P's length is 4. So I want to find the unit vector parallel to that. That is 1 over 4P. So it's done. Okay. It's a little bit, this one is a twisted. It's twisted. How do you get the unit vector? So the answer is still a vector in terms of P and Q. And then it's just shorter. Okay. With the practice, you go. Okay. Now again, there's a mistake here. Find the vector which is parallel to another vector. So the required vector is 1/8. Please check your answer with me. Next page. Next one is to prove there are two theorems saying that if there are two non-vectors and somehow their combination, this I call a combination. A and B are non-zero vectors, very non-zero, non-parallel. So these are two base vectors like that. One is A, the other one is B, like that. If their combination is a zero vector, this is a combination, which is I will extend A. For example, this is A. For example, this is A, this is B. So a combination is M times A and N times B. Just to extend them. So if their combination is a zero vector, now you can see from the figure that no matter how I extend A and B, these two vectors will never give you a zero vector. So if their combination is zero, that means the coefficients are zero. That's the only way to get zero. To prove it, it's like this. To prove it, it's like this. So if, because MA plus MB equals zero vector, that means MA equal N negative NB. Okay, so first case, if M is not zero, then A must equal negative N over MB. In this case, A and B are parallel. But it's given that A and B are not parallel, but given that A is not parallel to B, therefore M must equal zero. So my assumption is wrong. Theorem A. So if M is not zero, then A and B must be parallel, but they're not parallel, so M is zero. Okay. Now if M is zero, then negative MB equals zero vector, then M must equal zero. Now because here you can say that because B is not zero vector. Now how do you get a zero vector if B is not a zero vector? That must be N equals zero. Okay. So our proof is that M must be zero and N must be zero as well. Therefore, M must be zero and N must be zero at the same time. So this shows you that two base vectors, A and B, if you extend them either this way or this way, either way, no matter how you do it, Now suppose this is MA, this is MB. No matter how you do it, their sum should not be a zero vector. If their combination is a zero vector, that means you multiply them by zero. That means M is zero, N is zero, then it's zero. Second one. If there are two ways to express a vector using the base vectors, then the two ways must be identical. Now in math, it says that if this combination is equal to this combination, then the coefficients must be identical. So basically, if I have two, for example, there is the space vector A and B, okay? And there is another vector here somewhere. Oh, this is my vector, something. And this vector is equal to MA plus MB. Okay? And there is only one combination that can express it, not two. If the other one is also a combination, then they must be identical. There is only one way. Meaning that in the previous question, you see, when you have PM equal something A plus something B, you can only get this answer. It's not like, oh, if you use another method, you'll get another answer. There's no other way. The expression of a vector using base vectors is unique. Now, how do we prove that? It's actually not so difficult if we have the previous result, which is the combination can never be zero. Now, if MA plus MB equal MA plus MB, then MA minus M2A plus N1B minus N2B equals zero vector. Therefore, M1 minus M2A plus N1 minus N2B equals zero vector. Now, because a combination of two base vectors can never be zero unless M1 equal M2, N1 equal N2. So that's how it's done. That's how it's done. So there is only one answer possible. Next example. It is given that AB equal this and CD equal this and 2AB equals CD. There's no figure in this. It's just calculation. So because 2AB equals CD, therefore 2 plus 2 equals CD. Just put them in. And then there is a expression, a combination of A and B, but they are equal. That means the coefficients must be identical. Therefore, we have 2s plus 2 equal 3s minus 1 and 2t sorry, not 2t, 6t. 6t minus 2 must equal t plus 3. And then you can find the coefficients. S equals 3 and t equal 1. Kind of like the a polynomial is identical to another polynomial, then the coefficients must be identical as well. You have to practice this. Let me know when you're done. The answer is already there, right? This one. Yeah. Okay, last example. Now this example requires more, obviously the integrated skill. So far we have learned addition, subtraction, expression, and is even equality of expressions of vectors and how do you use it. In example 12.6, a triangle is given. C, D, and B intersect at F, and this ratio is given. It's unknown, but it's given. BD to DA equal 1 to N. Doesn't mean BD equal 1, DA equal N. It just means the ratio is 1 to N. 1 to N. The other side also the ratio is given. CF to FD. 1 to N. I don't know how to. You just have to memorize it, okay? If you mark it on the figure, it looks too much, huh? But anyway, there are two base vectors. Now, when two vectors are given, that means you don't need anything else. Do not introduce another vector. P and Q. P and Q. BA is P, BC is Q. I need to highlight them. BA is P, BC is Q. Okay? And also, BF is given. BF is given. BF. Anyway, we're going to use BF right now because expressing BF is way later. And then can we express BD? Can we express FD? And then can we find out M and N? Now, the intention of this question is basically like, I don't know if you have seen these types of questions before in the compulsory part, when you have, let's say, a triangle, and then I say, oh, here, this is 1, 2, 3, 1 to 2 maybe. The ratio is 1 to 2. And this side, okay, I draw another side. Oh, maybe this ratio is 1 to 1. Okay. Now, can you find the ratio of here and here? Now, that will be the question. Oh, sometimes I ask you this. I think the classic way is the area ratio. What is the ratio between this triangle and this triangle? Now, this is basically where this question is from. When in the figure, some ratios are given, can you find the ratio of other length? Okay. Now, using vector, it will be incredibly simple if you know how to use them. Now, you don't have to think about the angle, the parallel, the similar triangle, or anything like that. In the vectors, you only have to think about how to express them. Now, because this is the first example, so there are some guides. So you have A1, A2, and B. But outcome is, now the final outcome is that you will find the ratio. You see, the final question is to find M and N. If you find M and N, then you find the ratio. Okay, so let's see how we solve it. Hey, remember, you're just expressing now. You're just expressing. Don't worry about the angles and anything. Just using the vectors. First, BD. The BD is on P, right? So BD, easy. BD. because BD is parallel to BA. So that is BA divided by 1 plus N. So that is 1 over 1 plus NP. You're done. So this is a very simple vector. It's parallel to P, so it's something times P. Second vector. FD. The FD obviously is more difficult. FD. So I will use FD equal 1 over FD equal a ratio of DC because FD and CD are parallel. So it's M divided by 1 plus M CD. So FD is a part of CD. And the CD is CB plus BD. So that is M, 1, M, CB. CB is negative Q, and BD is found already. Is it correct? Check with me, huh? Check with me. FD is a part of CD. Okay? So it's a fraction of CD. And CD is CB and BD. CB and BD. CB is negative Q, and BD is found. No problem. So this is my answer, except that I have to express it this way. It's something Q plus something P. This is the standard expression. A combination of P and Q, basically. Now, B. Now, obviously, there are other methods, but here, by considering BD plus BF, BD plus DF, we just found BD-DF, right? Oh, we found FD, but BD-DF, express M and N. Now here, BD plus DF equal BD plus DF, which is the negative. P. Correct? I think so. So BD-DF is BD minus FD. So I did minus FD. So this one, after simplification, it should be, I put P together. So this is 1 plus N and 1 plus M. So 1 plus M minus N P plus M 1 over M 1 plus M Q. Yes, this is M. M. So this is 1 over 1 plus N 1 plus M P plus M 1 plus M Q. So it's expressed. Okay. We also know that BD plus DF equal BF. So this is actually BF. Okay. And BF is given. It's 1 over 12 plus 3 over 4. It's 1 over 12 plus 3 over 4Q. Okay. So the expression must be identical. I can solve equations to find the ratio. And right? I think so. So if you find m and then the value of m and then you know the ratio between AD and DB and CF and CD, that this vector method can help you find ratios at the same time. Remember in the compulsory part when you have to find the ratio one by one, oh, this is this and this one, you can find all of them other ones by solving equations. You need to practice. Let me know when you are done. Okay. Now, the difficult part of this, I think the first two you should be able to express. Now, it's just here that when you are doing it, you may not remember that you can introduce any number of unknown into this, and you can solve them all at once. So you can see, oh, there's an h, there's a k, but it will not matter. Now, by giving you this, FC is equal to HBD, it's saying that FC is parallel to BD. So it's actually more condition given. And AF, obviously, AF is parallel to AE. AF is equal to KAE. So F is on AE and CF is parallel to BD. So these are given more conditions added. And then you should be able to, oh, this is fine. As long as we know they're parallel, so expressing H is fine. As long as we know they're collinear, then there's a K, that's okay. So you must be okay. Oh, there are more than two there. I think if you consider B and C, the vectors are also unknown. So it's a lot of unknown in this. But in the end, the coefficients can be found. So the tricky part is that they can be found at the same time. So that's it. I'll see you on Monday. Bye-bye.